In this paper, we delve into the understanding of how the Iterative Contextual Learning (ICL) algorithm maps a set of demonstrations to a function on a query. We propose a hypothesis class view of ICL, aiming to dissect the mechanism of ICL into two parts: a learning algorithm and a rule application. The learning algorithm maps the set of demonstrations to a task vector, independent of the query. The rule application then maps the query to the output based on the task vector. The mapping from the set of demonstrations and the query to the predicted output is represented as a function of the task vector and the learning algorithm applied to the demonstrations. We propose an implementation of the hypothesis class using a transformer architecture, where the first few layers calculate the task vector and the remaining layers take the query and task vector as input to produce an output. We propose a procedure to tackle the challenges of dependencies between the demonstrations and the query. By introducing a dummy query and patching the task vector in the forward pass of the transformer, we maintain the high accuracy of ICL. We also dissect the network to eliminate undesired information flow and isolate the components of the learning algorithm and rule application in the forward pass. This modification allows us to validate our proposed mechanism. Our proposed separation of the learning algorithm and rule application provides a good empirical approximation of the ICL process. We demonstrate this by comparing the accuracy of our proposed procedure to a regular forward pass performing ICL, and show that our procedure maintains around 80 to 90% of the accuracy. We validate the robustness of the task vectors by conducting analyses. We show that the task vectors form distinct clusters and remain stable across different variations of the demonstrations and query. We demonstrate that the rule application mainly relies on the task vector and largely disregards the demonstrations. We show this by conducting a conflicting forward pass, where the model performs a task different from the one demonstrated by the demonstrations, but still achieves high accuracy corresponding to the injected task vector. We provide evidence supporting the interpretation of the task vectors. We show that the top tokens in the distribution over the vocabulary induced by the task vector directly describe the task, even if they did not explicitly appear in the context. We discuss the emergence of ICL as a capability from pre-training and relate our work to meta-learning in transformers and other related studies. We provide insights into the importance of training data structure and highlight the connection between ICL and gradient descent in language models.